This question is a bit deluding, you could say. The numbers here, which are in front of you, are not important. But you probably already figured this out. We're trying to find the valid statement out of these four. Which one is valid in the sense that it is well-defined? Well-defined in the sense of matrix multiplication. You see, matrix multiplication has some rules and regulations which we must follow. And that is, you start with the conceptual understanding of a matrix as a linear map. This is a linear map. It has dimensions 3 times 2, so 3 rows and 2 columns, which means that it takes a 3-dimensional vector as input and outputs a 2-dimensional vector. I proceed similarly for B and C. So B is a matrix, takes a 4-dimensional vector and outputs a 2-dimensional one. C is a vector that takes a matrix that takes a 3-dimensional. Actually, you could say this. You could say that it is a matrix in the sense, or I mean, it is a vector, yes, but a vector is just a matrix which takes, in this case, 3-dimensional vector and outputs a 1-dimensional vector. You should think about this for a moment. This is just a dot product. It's just a dot product. If you take a vector with a vector, you multiply them by each other using matrix multiplication. It's just a dot product. You can check this yourself. Maybe try to compute C times, well, not C times C, C times C transpose. Right. Very important. So maybe you can try to do this. Check that this is indeed. Oh, no, not C times C transpose. It gives you a 3-dimensional matrix. This is horrible. You should do C transpose times C. Because then the output is 1-dimensional. This is the dot product. The other one is just horrible. So just be careful, you know. Matrix multiplication is non-commutative. So C transpose is not equal to C transpose C. Anyway, so this is here. And we want to see which one is valid. To do this, I think it is a good idea to first compute the dimensions of the transposes of each one of these matrices / vectors. B transpose is a 2 times 4 matrix. This is a 2 times 3 matrix, and this is a 1 times 3 matrix, you could say. And the reason for this, if you've never ever seen this before, you could think of this as a 2-dimensional, and this is 3-dimensional. Then you just flip it. This is what the transpose does. It puts the rows instead of the columns, and the columns instead of the rows. We have 2 rows and 3 columns. Now, when I flip it, I want you to count how many rows are there, how many columns are there. Well, I think it is clear now. And it is 3 and 2. 3 rows and 2 columns. So everything is transposed. If this is your matrix A, then this is your matrix A transpose. Very good. Now let's see which one of these is defined properly. So A transpose B transpose. A transpose takes a 2-dimensional vector as input and outputs a 3-dimensional vector. And B transpose takes a 2-dimensional vector as input. So the input the output from here does not match the input from there. This cannot be the solution. For the next one, C transpose is 1 times 3, takes a one-dimensional vector, you could say, and it returns a three-dimensional, it returns something that is three-dimensional. And so you do this, then you compose it with B transpose, which takes 2 as input, two-dimensional. And if it takes a two-dimensional as input, then it is a problem, right? Because 3 does not match with the 2, so this cannot be a solution either. Then C considers the vector, the linear transformation matrix B, and it composes it with A transpose. So it takes an input of 4 dimensions, it outputs 2 dimensions, and then you go to A transpose, which inputs 2 dimensions, it outputs 3 dimensions, and now finally you take this 3-dimensional output and you input it inside of C, so it matches and it gives you something that is 1-dimensional as output. Maybe I'll draw this using the highlighter. I think it will be very elegant and this is too light. Perhaps I should use more stronger opacity. So we said B and then A transpose and then C. So it flows very nicely, as you can see. This will be the answer, and there is nothing else you can really do about this problem other than to know the basics of transposing a matrix, to have the conceptual understanding of what a matrix is as a linear map that takes certain input and outputs certain output, and then apply that in this very specific context. So this is not the only valid matrix multiplication, but it is one of them. So if we check A, B, C, we will find that we have 3 times 2, and then B is 4-dimensional, so it doesn't work. But this one does. Lucky for me, because then I don't have to reshoot this video once again.